Hello, everybody. Thank you for the opportunity to present to you the electrochemical processing research and development program in the Office of Fuel Cycle Technology in the Office of Nuclear Energy. And my name is Stephen Kohn, and here is my contact information. Here is my address, email address, and the phone number. Before we start, I'd like to emphasize one thing here is when we say electrochemical processing, we can interchange with pyroprocessing. People sometimes call it pyroprocessing. So it's pretty much the same thing for us in the program. Within the Office of Fuel Cycle Technology, we have an integrated approach to address broader R&D area, which include the front end and the back end. In the front end, we have the uranium resource and the fuel fabrication program. And in the back end, we have interim storage and the recycle and disposition programs here. And in the fuel resource, our focus is on unconventional uranium production. Specifically, it's about the uranium extraction from seawater. In this case, later this afternoon, around 4:20 p.m., we will have a special section to talk about this solicitation in this area. And earlier this afternoon, you may have heard about the fuel fabrication fuel program already. And then in the back end, we have interim storage, recycle, and disposition. And I will focus on one of these recycle separations under this separation program. Later on, following this presentation, Dr. Jim Brzee will talk more broadly about separation program. That include aqueous separation and also the waste form. So within the back end of fuel cycle separation technology program, our goal is to develop advanced fuel cycle technologies, including aqueous separation, electrochemical processing, and waste forms. Our objective is to improve current fuel cycle performance and enable a sustainable fuel cycle to minimize the process and to minimize the waste generation, also potential to reduce the material diversion issue. So have a broad range of separation technology are being investigated to support modified open and full recycle options. Also, we are focused on understanding the scientific fundamentals of separation methods. And key technology challenges in this case will include economical recovery of transuranic elements for recycle and transmutation. And also, we want to focus on minimization of waste, including both low and high-level wastes. For the general R&D opportunity areas, the first item is experimental collection of fundamental data to characterize and quantify chemical processes, validation of modeling approach to develop a better understanding of separation method. The second item is develop novel transformational separation technologies that have the potential of significantly reduce cost of processing. And the third item is develop innovative materials to meet the specific requirement of advanced separation systems. In this case, we want to either through electrolytes or the crucible containment. So our goal is to increase the durability or trying to find a better or cheaper material. And the last item is develop a alternative waste form that have the potential of significantly decrease waste loadings and increase durability over borosilicate glass. Specifically, three major interests from university community we like to solicit. The first one is in the area of electrochemical processing. The first one is phase equilibrium data. And the second one is thermodynamic properties. And the third one is innovative process. The first one about phase equilibrium data. We like to deduce phase equilibrium in binary in the higher order of molten salt systems that contains actinide and lanthanide halides. So our goal is to provide insight into solvent-solute interactions and the thermodynamic property of the systems. In this case, we like to obtain new data to help resolve existing conflicting results, as that's shown in the bottom two figures. Sometimes they have inconsistent data in the literature. We like to find to better understand the system. The second item is explore existence of compound formation, identify decomposition mechanism and decomposition temperatures. The third item we want to emphasize is the programmatic emphasis. You can propose different systems, but we do like our current program emphasis in this case is the lithium chloride and the lithium chloride potassium chloride system. If you like to propose different molten salt systems, please justify for that. The second item we are specifically interested in is thermodynamic properties of transuranic elements in molten salt system. Our goal is to facilitate our enhanced predictive model and separation process development. In this case, the property of interest include electrochemical potentials, activities, and activity coefficients, and transuranic halide in molten salt. And the range of condition may include, say, in 15 weight %. We don't like you to propose something really high percentage. Then in that case, it's not really relevant to our program needs. And the temperature, we like to have to about 500 to 650 degrees Celsius range. So in the bottom picture, you can see if you can help to develop a deposition potential for uranium or uranium, in this case, will be very useful to our program. And the third item, the last item we are interested in is the innovative processes. In this case, we like you to help us to develop novel alternative molten salt-based separation method, which may lead to significantly reduce the process complexity, results in potential cost reduction, reducing potential proliferation risk, and minimize waste generation. Example may include actinide recovery from used fuel, actinide removal from molten salt waste streams, and fission product recovery from molten salt solvent, thus allowing salt recycling. So basically trying to reduce the cost. That's pretty much for the electrochemical processing solicitation priorities for this year. And we appreciate your interest in supporting our program. If you have any questions, please feel free to contact me or contact Mark Williamson of Argonne National Laboratory. And I would like to entertain questions if we still have time.
Hello, I'm Jim Brazee, the Federal Program Manager for Separations and Waste Forms campaign in the U.S. Department of Energy, Office of Nuclear Energy. Delighted to have an opportunity to talk about our research program and our research needs. And I very much look forward to cooperative activities with members of the universities and colleges of the United States. Our overall campaign objective is to develop separations and waste forms technology that will improve our current fuel cycle. The current fuel cycle in America is really the once-through cycle in which nuclear fuel is burned in a nuclear reactor to produce power and then is stored and disposed of. In many other countries in the world, that fuel cycle program is broadened, and it may ultimately be done so here in America. Meanwhile, what we're trying to develop is options for the future where we may have the ability to choose between the so-called open cycle, which is once through, or a closed cycle in which the fuel is repeatedly recycled and some of the unused energy contained within it is captured. Those decisions have not yet been made. We simply are trying to lay a scientific foundation for such a decision if it were made. I have a cartoon here which illustrates very broadly the areas of research interest that I'll be talking about. We're principally interested in understanding the separations processes in detail. Those processes which will give us the ability to recycle such materials as neptunium, americium, and curium in future fuel cycles. We're also very interested in improving our off-gas management. As you know, there are a number of radioactive materials which are emitted when nuclear fuel is dissolved. Among them, radioactive iodine, tritium, carbon-14, krypton-85. These materials are somewhat difficult to manage, particularly to try to capture and then retain them in a stable waste form. So I'll be discussing that a little bit more later. I also show in this cartoon what is labeled an FR fuel separations. You've just heard about that. That is likely to be, in the future, fast reactor processing by electrochemical or pyrochemical processing. And Dr. Stephen Kung just discussed that with you. But you'll see also in the cartoon waste forms and processes. That's a very broad issue affecting all streams that may be coming out of a separations plant, whether they're low level, medium level, or high level, whether they're solid, liquid, or gaseous formed. And what we're trying to do, as the cartoon illustrates, is to develop enough knowledge of the technologies to make them available for industrial deployment sometime in the future. I'll quickly go through the major areas of our overall research program and then focus on two that I think we'd be particularly interested in getting proposals from universities and colleges. Broadly speaking, I'll be talking about advanced aqueous processes. Aqueous processes are those which are currently being used throughout the world. There are major aqueous separations processes in France, in Great Britain, in Russia, in China, in Japan, in India. So there's a lot of interest in that technology, and it's capable of considerable improvement over the coming years for its application in America. Enabling technologies are principally aimed at minor actinides separations. These are those other than uranium and plutonium, the ones you hear the most about. Neptunium, americium, curium are of considerable interest because they represent a large heat source in the solid waste that ultimately goes to disposal. They also can provide energy. The off-gas activities I already mentioned. We're particularly interested in getting universities assistance in understanding the fundamental science underlying all the processes that we'll be discussing. We'd like really to be in a position to model and predict behavior of the various materials in the processes in some detail. Ultimately, I think it would be nice to be able to derive a mathematical model of a complete separations plant, which will allow you to predict the performance at all places under all conditions. This would be particularly helpful in trying to develop our improved understanding of proliferation and diversion. We're also interested in alternative processes, and this is where ideas such as the use of ionic liquids might be applied as an alternative to conventional solvents or even to conventional electrochemical processes. We're very interested in new ideas in the area of waste forms. We particularly like to have an improved understanding of surface processes associated with with waste dissolution. We'd like very much to know in some detail what happens when, for example, pyro processes develop a particular type of waste form and it's subjected to some type of corrosive environment. We're interested in uranium from seawater. You'll hear more about that later in the presentations. And fortunately, we have already had a good coverage of our electrochemical processes by Dr. Stephen Kung. Let me now talk in some detail about the scientific basis for aqueous separations. We do not thoroughly understand the conditions under which the various oxidation states of the minor actinides are stable. Neptunium in particular is a difficult material to handle. It can exist in a number of different valences simultaneously, and the valences themselves determine the separations process and its effectiveness, which is why we need improved understanding of the conditions under which the oxidation states of the various actinides are controlled. We'd like very much to have help from our university colleagues in understanding the kinetics of the various processes of interest to the separations process. We have a number of different processes well described in the literature. Many of them are kinetics driven. That is, the effectiveness of the process depends upon the kinetics of the particular chemical separations occurring at the interface. And a thorough understanding of those processes would be of extreme help to us. In the waste form area, our focus would be not only on the off-gas systems, and I mentioned earlier iodine, technetium is another very difficult material to handle. It can exist in vapor form as well as solid and liquid form. Over geologic time frames, improved understanding of processes are needed because we're dealing with wastes which may be subjected to control, environmental control, over hundreds of thousands of years. So the more we understand the basic processes and their kinetics, the more we understand the corrosion processes that occur at the surface of waste forms, the better we'll be able to predict and understand what might happen over hundreds of thousands of years. So we'd like to invite proposals to increase our understanding in that area. I'll summarize what I just discussed briefly on this view graph. We have valued very much the partnership we've had with universities in the past in improving our basic understanding of separations processes and waste forms. I believe the areas that I just highlighted are particularly suitable for university research, and I would invite a broad response to that particular request. We have worked very successfully in the past with universities. We look forward to more of that in the future. And I'll invite your questions now on any part of my presentation.
Okay, the first question is, do you know what the budget will be for this program yet?
What the what?
What the budget will be?
Oh, budget situation is quite unclear. We are, as you probably have read in the newspapers, in a period of great uncertainty about fiscal 14. Our budget, for example, in the Office of Nuclear Energy could be anywhere between $90 and $150 million. And so there's great uncertainty about our particular level of funding for our ongoing research activities at national laboratories and through contract. All I can say is that whatever it finally comes out, we will be devoting 20% of that budget to university research.
The next question. You mentioned uranium recovery from seawater as part of the separation scope. Should proposals for uranium and seawater be submitted in separations or in fuel resources?
I think we're actually classifying that in the university programs as fuel resources. But you'll be hearing more about that. That subject will be covered later this afternoon.
In your estimate, what reasonable funding level would be proposed with the high cost of experimental facilities necessary? Well, let me reword that. With the high cost of experimental facilities that are necessary, in your estimation, what funding level would be reasonable for the proposal?
Goodness, that's a very wide open question. It depends obviously on the scope of the work and the requirements for experimental work if necessary. I can imagine very useful research proposals which do not necessarily involve experimental effort. They could be a modeling effort based upon existing data. So I can't answer the question the way it was put to me, but I will say this, that we take into consideration the reasonableness of any proposal based upon its requirements, and where those requirements do indicate, for example, a specialized experimental facility is needed and would be broadly available to the university for research beyond this particular program, we will take that into consideration.
Let me just add real quick to what Jim said. You can buy equipment through our standard R&D proposals and awards, a total of $800K. But even more importantly, you can couple the equipment buying with the GSI program to get additional resources for an R&D project if awarded. So that could be anywhere on the order of $300K or more in addition to what you would get through the standard R&D award. So, and even more if you're able to match. So I think there's a strong possibility to increase experimental capability with equipment and so forth in our program.